Alright, this is John White, Breaking Mad, talking about Friedel alkylation, mainly making P2P. Here's the formula for it. All you need is benzene, bromoacetone, a tiny bit of anhydrous iron bromide, and do it at 0 degrees C, and you'll make P2P and HBr. Let's go over the mechanism first, though. Okay, first of all, I'm going to go over a regular Friedel Crafts alkylation with no carbonyl group on the... See how I got 3 carbons here, but I don't have the carbonyl group, right? I have the bromine. Let's go over the simple part first so we can understand the mechanism. Now, the bromine is electronegative, so it's going to pull electron density towards it and make this carbon positive, right? This benzene is neutral, but it has a lot of electron density above and below the plane of the molecule in the pi electrons. In the pi orbitals, right? All those pi electrons are, a lot of electron density is there. So these two should react. You got a delta positive charge, and you have a lot of electron density, but they don't, because they don't react because benzene is aromatic, and that's a special kind of stability. So to break that stability, you would need more positivity over here, or you'd need to activate the ring more. Let's go over how we can make this more positive, because we don't want more stuff on the ring. We don't want to activate it. We want it empty. So let's figure out how we can make this more positive, this carbon, so it's more positive enough to attack, so this benzene ring can attack it. Okay, here's your bromopropane, or propyl bromide. And you can see the bromide is surrounded by electrons, right? Now that's why we have to put the iron tribromide in there, is because it is a Lewis acid, and as a Lewis acid, it has empty orbitals, right? It's got the 3. I'm guessing on this here. I didn't look this up, but I'm just guessing. The bromine goes in the paper, this one comes out, and the rest is on the paper. So it'd be like a flat molecule like that, with a like this, and then you got above and below it. You got an empty orbital there, right? That can be filled. And if you count these two, you got 1, 2, 3, 4, 5, 6. That doesn't sound like a good octet. So it can take electrons into the empty orbital, right? And it does from the bromine. See how I have the arrow? When that happens, the bromine comes off, right? Right here. And now you have, instead of 3 bromines surrounding this iron, you have 4, right? And it becomes a negative anion, right? And what's left would be this propane or propyl group, because it's positive, right? It's counteracting this negative ion here, right? Here's your positive, here's your negative. So now, instead of a delta positive like over here, right, a partial positive charge, you have a full positive charge, a full cation, a lot more positive, so that it can react with the double bond, with the aromaticity of the ring, right? There's only one problem, is because there is carbocation formation, there's carbocation rearrangement. And what would happen on this specific example is you would have a hydride shift, right? And your positive charge would go over to where the hydride used to be, which would be right here, because it's more stable. And then when it adds to the benzene group, it would add like that, see? Instead of like this, which originally, because originally the positivity was right here, but it moved. This won't happen. This happens because this carbocation is a lot more stable. And that's how it will add, like this. So that's one problem with this reaction, okay? Now, how can you stop that from happening? Well, let's look at one way. All right, first let's finish the mechanism. The positive carbocation attacks, well actually the benzene attacks the carbocation. Now you have a hydrogen and the carbocation. You have a lot of positivity. So remember, you have that iron tetrabromide that you made, remember? And it's negative. So it comes and it grabs this proton off, and now you have your product. Now in the process, you make HBr, right? Because you have an H here that you took off a proton, and one of these bromides come off. And if you remember, you started out with iron tribromide. So when this bromide comes off, you just made your catalyst again. Your catalyst has been reformed. And that's why you don't need that much catalyst. Like if this is a Friedel-Crafts acylation, then you need a stoichiometric amount of this catalyst. But in this, because there's no carbocations in that reaction. In this reaction, there are carbocations. So you only need a small amount of this catalyst because you'll be reforming it as you make it. And trust me, you don't want this reaction going fast, you know what I mean? You only want it to go slow because it's so exothermic, you know what I mean? The less, you know, if you put in a stoichiometric amount, it'll all happen at once, man. You just flood your reaction with heat because it's so exothermic. Okay, here's your carbocation, and here's your rearranged carbocation. Now look at us though. When we make our carbocation, we're going to have this carbonyl group on there, right? And because of that, these electrons in the double bond can jump down and form a double bond here, and your positivity would go up onto the oxygen atom, right? Because you got, if you look on a periodical chart where it shows you neutral radicals, you'll see that oxygen is in group 6, so it needs 6 electrons to be neutral. It has 1, 2, 3, 4, 5. Doesn't have enough electrons, so it must be positive, right? And since oxygen doesn't really like to be positive, it's mostly around this resonance, but it goes back and forth in between these two, or it's some type, you know what I mean? It's a hybrid of that. So anyways, because of that, this is resonance stabilized at that point, right? It's a good, you know, stabilization of this carbocation. It doesn't need to rearrange. It's better off being where it is, and you know what I mean, and having this resonance. So the rearrangement won't really happen. Plus there is no hydride on the carbonyl carbon, so there can't be any hydride transfer. Now another problem with this reaction is over-alkylation. See, once you make your product, whatever it is, you know, you're adding an alkyl group, and an alkyl group is an electron donating group, and that activates the ring, because the reason why this reaction is happening is because you have a positive carbocation, and even though it's neutral, the benzene ring has a lot of electron density, which is negative. That's why the reaction happens. So if you have a group attached to the benzene ring that can donate electrons into the ring, that makes it more negative. That makes it more reactive, right? And you'll end up doing this. You'll end up adding twice. Now, since it's an alkyl group, it's going to be an ortho-para directing group, but the ortho positions I doubt it would add to because of steric interference. I think you'd have pretty much all of it be para position if you had any kind of over-alkylation. How do you stop that from happening? You can't, but you can cut it down a lot. Just add in twice as much benzene as you need. That way, let's say you're almost done with your reaction, right? Well, if you're almost done with the reaction, then that means that there's hardly any benzene in the pot, and it's all P2P. What do you think is going to happen when you're creating these carbocations, to make the P2P. First, 10% of it is benzene and 90% is P2P. What do you think it's going to add to? It's going to add to the P2P. You're flooded with P2P at that point. You know what I mean? Even after half the reaction is over, you got a 50-50 ratio now of P2P and benzene if you use 1-to-1 molar ratios, right? And the P2P is more reactive, so it's going to add to that at that point. But if you add double the amount of benzene, now, even at the end when you got 90% of your bromoacetone is gone, you know what I mean? It's all reacted. Now, instead of just having 10% of the solution being benzene, you added in an extra mole. So now you got a whole mole plus that 10%. Now it's still got a better chance of, or at least a good chance of finding a benzene ring to add to, instead of adding to the P2P ring that you already made. Now this reaction is very, 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 very exothermic, okay? Okay, so let's go over the instructions, and keep in mind this is all guesswork here. I mean, there are facts. Like when I say cool everything down, it's exothermic. I mean, those are actually facts. And about adding the extra benzene, you can see I have the equation up there, and I show that I have twice as much benzene as I need, 2 moles compared to 1 mole of the bromoacetone. First thing you want to do is cool everything down to 0, man. You want the reaction to be at 0. You want it to be cold. You know what I mean? You actually want to cool your stuff down below 0. So when you do the reaction, the heat will, eventually bring it up to 0. So this is how you want your setup. Basically like a reflux. You can see I got the thermometer in there. You got your ice bath. If you can get something that'll be a colder ice bath than salt water, that'd be best. When I try this, I'll probably just use salt water. The reaction hates water, actually in the pot. So that's why you need to everything, dried out, the benzene, the acid, the bromoacetone, and you want anhydrous iron bromide, tribromide. So anyways, you freeze everything down, and you mix your 2 chemicals, in the round bottom flask, your benzene and your bromoacetate, to a freezing flask. Everything's chilled down. Then take out your thermometer and add in a little bit of anhydrous iron tribromide. It might take, if you put it in and then you close up the thing and you're like, whoa, nothing's happening, give it a few minutes. It takes a while sometimes for the reaction to start. But it's happening because it starts bubbling, because you're making HBr, and the HBr is not soluble in the non-polar products that are in there, like the benzene. So it'll bubble out, you know what I mean? Just like when you make CO2, it bubbles out of solution. And that's how you're done too, you know what I mean? You don't want to put all your FBR3 in all at once, you know what I mean? Put a little bit in, and let the reaction go a little bit, then put a little bit more in, let the reaction go a little bit, and then put the rest in, you know what I mean? You don't want to just dump it all in at once. Unless if you're doing like micro reactions, you might say how much you put into the salt. Well, if you're doing little micro reactions where you're just making a few milliliters, you just need like you ever see a grain of salt or a grain of sand from like a beach or something? That's all you need. If you're doing like in test tubes, you know what I mean? You're just making milliliters of stuff. That's all you need, a little tiny grain of sand about that size. If you're doing more than that, maybe 20, 40 milliliters you're trying to make or something, like a hobbyist would do, then, you might need a half a gram or something, you know what I mean? Like what you would call a pinch. If you were cooking something, you'd say, put a pinch of salt in there. That would be, how much you can pinch in between 2 fingers, and, that's a pinch. The truth is, I don't know exactly how much, the iron tribromide to put in, but I know it is very, very, very little. Don't miss part 2.